I want you to start off today by just imagining something truly terrifying. Like, picture the most indestructible, relentless biological agent known to modern science.
Which is a pretty dark place to start, I know.
Yeah, it is. But, you might immediately think of a virus like Ebola or maybe some highly mutated antibiotic resistant bacteria. But it's actually something much simpler. And because it's simpler, it's so much stranger. I want you to imagine prions.
And that is a really profound place to start, actually, because prions, um, they challenge our fundamental understanding of what a disease even is. I
Yeah.
mean, they aren't alive, they don't have DNA, they don't have RNA.
Right. They are just misfolded proteins. They're the agents responsible for those incurable neurodegenerative conditions, things like mad cow disease. And the terrifying part is really how resilient they are. You can't kill them by cooking them. You can't irradiate them.
You can't scrub them away with bleach either.
Exactly. They are essentially a biological glitch, like a tiny molecular machine that gets stuck in the on position, and it just slowly, inevitably converts every normal protein around it into a tangled copy of itself. Now, the reason I am asking you to imagine this absolute nightmare scenario is because of a document that recently crossed our desks.
It's a fascinating document.
It really is.
Yeah.
I want you to imagine that this exact same biological glitch, this indestructible self-replicating structure, actually holds the master key to our entire future civilizational infrastructure.
It requires a massive cognitive leap. I mean, we are so conditioned to view prions strictly through the lens of pathology. They are terrifying, precisely because of that resilience you just mentioned.
Right.
But when you step back and strip away the disease aspect, when you just look at the underlying physical architecture of how these molecules assemble and hold themselves together, you are looking at an absolute marvel of molecular engineering.
Which is exactly the premise of the grounding material for today's deep dive. We are exploring a fascinating, incredibly dense manifesto from March 2026. It's titled Prion and Amyloid Architectures, a Total Application Framework.
Written by an independent researcher named Zachary David Enfield.
Yeah, Enfield.
Oh.
And he essentially asked, what if we stopped trying to cure this glitch and started trying to build a civilization out of it?
Enfield's work is really a synthesis. He has taken roughly 2 decades of peer-reviewed experimental literature spanning material science, synthetic biology, molecular computing, and even theoretical propulsion physics, and woven it into one coherent design framework.
It's a lot.
It is. He argues that the structural logic of a prion is the ultimate raw material.
Okay, let's unpack this. Because if we are talking about building everything from quantum computing networks to self-healing spacecraft hulls and even the food on your plate, we really have to understand the nuts and bolts of the material itself. You mentioned the physical architecture. What is actually happening at the molecular level that makes a misfolded protein so indestructible?
Well, it all comes down to a specific structural motif. It's called the cross-beta architecture. This is the foundational shape shared by all prion and amyloid fibrils.
Okay.
To visualize this, we have to look at how proteins normally behave, right? Usually a protein folds into a very complex, globular, three-dimensional shape. It looks like a tangled up ball's yarn. And that specific shape dictates its exact function in your body.
And if it loses that shape, it stops working. Like when you cook an egg, the heat breaks the weak bonds holding the protein together, it unravels, and the clear egg white turns solid white. That's denaturing.
Exactly. Globular proteins are relatively delicate, but the cross-beta architecture is different. Instead of a tangled ball, imagine taking stretches of the protein chain, which we call beta strands, and laying them out flat, side by side.
Oh, okay.
Yeah, they orient themselves horizontally, perpendicular to the long axis of the fiber they are forming.
So it's like stacking planks of wood to build a long walkway?
Yes, but it is how those planks are fastened together that really matters. These horizontal beta strands are locked to one another by a dense, repeating network of hydrogen bonds.
Wait, hydrogen bonds? I mean, individually, those aren't the strongest bonds in chemistry, right?
Right, they are essentially just weak electrostatic attractions between molecules. But when you layer them in this massive, highly ordered, repeating geometric grid, they become incredibly rigid. They form flat, stiff planes called beta sheets.
So that rigid sheet acts as the frame of the material. But, if a material is just rigid, it's usually brittle, like glass. If you hit it, it shatters.
Which is where the second component of the architecture comes in.
Yeah.
Between these rigid beta sheets, you have the side chains of the amino acids.
And the building blocks.
Right. Amino acids are the building blocks of the protein, and each one has a little chemical appendage hanging off it. In a cross-beta fibril, These side chains protrude outward into the space between the sheets. And these side chains are flexible. They act as microscopic shock absorbers.
I'm trying to picture this mechanically. It sounds like a nanocomposite material, like how we build a skyscraper using concrete and steel rebar.
It is the exact same mechanical logic, just operating at a scale of 10 nanometers. When physical stress is applied to the amyloid fiber, the rigid hydrogen-bonded sheets provide the stiffness and the tensile strength, the steel rebar, essentially.
And the flexible parts.
Meanwhile, the flexible side chains dissipate the kinetic energy. They absorb the shock so the rigid frame doesn't snap.
Which we see in nature all the time, honestly. Nacre, the shiny mother of pearl on the inside of an abalone shell, works like that. Or even the tendons in your own body. They combine rigid elements with flexible elements so they bend instead of break.
Exactly.
But nacre is macroscopic. You can hold a shell in your hand. Here we are talking about structures built molecule by molecule. How strong are we actually talking?
The measured mechanical performance is staggering. In-field sites work by researchers like Knowles, who engineered polymeric amyloid fibers using 128 repeating sequence blocks. When they tested the tensile strength and toughness of these engineered fibers, they hit a toughness of 160 megajoules per cubic meter.
Wow. I need a benchmark for that, though. What is 160 megajoules per cubic meter in practical, everyday terms?
Well, spider dragline silk has long been considered the absolute holy grail of tough biological materials. It's the silk spiders use for the outer rim and spokes of their webs, engineered by millions of years of evolution to absorb the impact of flying insects.
Right, the really tough stuff.
Yes. And spider dragline silk peaks at around 150 to 160 megajoules per cubic meter. So, synthetic engineered amyloid already matches or beats the toughest biological material on Earth.
That's insane.
But the real revelation is the density. It achieves this extreme toughness at 1/8 the density of structural steel.
Wait, 1/8 the density of steel, but tougher than spider silk.
What's fascinating here is the circumvention of traditional material trade-offs. In conventional synthetic materials, you are constantly playing a zero-sum game. If you want a polymer or a metal to be stronger, you almost always have to make it heavier, denser, or more brittle. If you want it to be incredibly lightweight, you sacrifice durability. Amyloid architectures achieve extreme toughness, ultra-low weight, they're entirely biocompatible, and they self-assemble in water.
So you do not have to forge them in a giant furnace.
Exactly. You just grow them.
And according to the manifesto, you can tune them too. Enfield talks about something called the hydrogen bond density dial, or the HBD dial. It sounds like he's saying you can just turn a literal knob to change the physical properties of the fiber.
It is a really powerful conceptual model
Yeah.
because the core mechanical strength relies on that incredibly dense network of hydrogen bonds holding the beta sheets together. Researchers can basically dial in the exact material properties they need simply by changing the amino acid sequence before the protein is even synthesized.
Okay, so if you program a sequence that packs the amino acid residues extremely tight,
You maximize the hydrogen bond density. The resulting material behaves like a nanoscale structural steel beam, stiff, unyielding, perfect for bearing heavy static loads.
but what if you dial it the other way? Like if you deliberately introduce sequences that don't pack together perfectly?
Then you decrease the hydrogen bond density.
Right.
You introduce polar regions or slightly disordered sections into the core. The material becomes more dynamic. It actually becomes a bit more fragile and responsive to its environment.
Wait, why would you ever want to engineer a super material to be more fragile? That seems counterintuitive.
Because a fiber that is easier to fragment is a fiber that can replicate faster.
Oh.
Yeah. When these fibers break, the exposed broken ends act as templates, we call them seeds, that recruit more free-floating proteins to grow new fibers. If you want a dynamic, rapidly growing, self-assembling scaffold that can adapt to a changing environment, you actually want it to fracture under specific conditions so it can multiply. It is programmable structural biology.
Okay, the mechanical strength makes sense. The composite nature makes sense. But I'm still stuck on the chemistry here. At the end of the day, we are talking about a protein. It is made of amino acids. It's essentially the same basic biological stuff as my skin or a piece of chicken.
True.
So how does a protein survive the conditions Enfield lists in this framework? He mentions these structures surviving pure formic acid, concentrated sodium hydroxide, being boiled for hours, and taking massive doses of gamma radiation. If I drop a regular piece of chicken in boiling acid, it dissolves into mush. How does this not just melt or break apart?
It is the defining paradox of the material, honestly. And it really highlights how unique the cross-beta structure is compared to normal biology. When you think of a protein dissolving in acid or being digested by an enzyme in your stomach, what is actually happening?
It's being broken down.
Right, but specifically, the acid or the enzyme is seeking out the peptide bonds. The peptide bond is the actual chemical link holding amino acid A to amino acid B. If you cut the peptide bonds, the chain falls apart. The protein is destroyed.
So how does the amyloid hide those links?
It is entirely about geometry. In a standard globular protein, those peptide bonds are often exposed on the surface, moving around in the solution, completely vulnerable. But when the protein misfolds and snaps into the cross-beta architecture, it reaches one of the lowest possible thermodynamic energy states available to it.
Meaning it's super stable.
Incredibly stable. It folds so tightly, and the hydrogen bonds layer so densely over each other that the vulnerable peptide bonds are physically buried deep within the core of the fibril.
Oh, wow. So it's not just a strong material like some kind of biological Kevlar. It's more like a Roman phalanx formation.
That's a great way to put it.
Like the vulnerable parts, the actual chemical links, are the soldiers, and they have completely locked their shields together. The acid or the protease enzymes are the enemy weapons, but there is literally no physical gap between the shields to get a sword through. The enzymes just bounce off because they can't access the cleavage sites.
That is a phenomenal analogy. Yes, the structure acts as impenetrable physical armor against chemical attack. And regarding the gamma radiation, which is an entirely different kind of threat.
Right, radiation usually shreds chemical bonds by blasting them with high-energy photons.
Exactly. But the dense, highly ordered, periodic crystal structure of the amyloid fibril allows it to absorb and dissipate high-energy impacts far better than a loose, amorphous protein. The energy is distributed through the lattice rather than breaking a localized bond.
That is just wild. We have a programmable biological thread that is practically immortal to chemistry and radiation, stronger than spider silk, and lighter than plastic. I mean, you could build bridges or space elevators out of that.
You really could.
But Enfield doesn't stop at passive building materials. This is where the framework makes a massive pivot. Because it's one thing to have an indestructible thread, it's an entirely different technological paradigm when you realize that this exact same biological thread can carry an electrical current and generate its own power. We're talking about the self-wiring world.
Yes, we transition from passive physical structure to active electronics. The framework notes that the foundational proof of concept for this goes all the way back to 2003. With a researcher named Scheibel. They worked with a very specific protein, a yeast prion known as SUP35.
Let's pause right there because the word prion sets off alarm bells for people. Just to clarify for the listener, this is a yeast prion. It affects single-celled fungus. It has absolutely zero biological mechanism to infect human beings or any mammal.
A crucial distinction, thank you. We are talking about the structural mechanism here, not mammalian disease. So Scheibel's team took this harmless SUP35 yeast prion and placed it in a solution, allowing it to naturally self-assemble into long fibers about 10 nanometers wide.
Okay.
But they went a step further. Through genetic engineering, they modified the prion protein sequence so that the outer surface of the assembled fiber would have specific chemical attachment points, essentially sticky molecular docking base.
Sticky to what, exactly?
To gold. Once the fibers had grown and formed a complex network in the solution, the researchers introduced gold nanoparticles. The gold nanoparticles ignored the water, ignored the container, and bound exclusively to those engineered attachment points on the protein fibers.
Wow.
Yeah, the protein scaffold physically arranged the gold particles into a continuous line, effectively metallizing the biological fiber.
Wait, they grew a wire, literally planted a protein seed, and watched a microscopic gold wire assemble itself.
They grew a wire that conducted electricity with incredibly low resistance. And to understand why Enfield places such emphasis on this, we have to look at how we currently manufacture electronics. For the last 60 years, the entire global economy has relied on top-down manufacturing.
Right, silicon chips?
Yes. We take a giant, highly purified ingot of silicon. We slice it into incredibly thin wafers, and then we use photolithography using lasers and harsh chemicals in multi-billion-dollar sterile clean rooms to carve tiny channels into the silicon.
It's basically microscopic sculpture. You start with a big block of material and you chisel away everything that doesn't look like a microchip.
Exactly. And as our chips get smaller, the lasers have to get more precise, the clean rooms have to get cleaner, and the energy cost skyrockets. It is an unsustainable trajectory. But the amyloid approach is bottom-up manufacturing. The wire templates itself.
It just
It
grows.
self-organizes from the molecular level up just by floating in a beaker at room temperature. You don't need a vacuum chamber, you don't need toxic etching chemicals, and you don't need a silicon wafer. The biological scaffold prepositions itself into the exact circuit layout you programmed, and the conductive elements just snap into place.
Here's where it gets really interesting. Because relying on gold nanoparticles is cool, but Enfield points out you don't even necessarily need the metal. He cites a 2021 study by Ships that demonstrates intrinsic conductivity. The protein itself, completely naked, conducts electricity.
This relies on a quantum mechanical phenomenon operating within the material. The mechanism is called tyrosine hopping.
Tyrosine hopping,
Yeah.
like the amino acid.
Yes, tyrosine is one of the standard 20 amino acids that make up proteins. What makes tyrosine special is its physical shape. It contains an aromatic ring, a tiny flat hexagon of carbon atoms. In certain engineered amyloid sequences, these tyrosine rings end up stacking perfectly on top of each other down the central core of the fiber.
Like a stack of microscopic coins. But why does stacking them make them conduct electricity? A stack of plastic coins doesn't conduct electricity.
Because of what is floating above and below those flat carbon hexagons. In an aromatic ring, the electrons aren't strictly locked to individual atoms. They form these diffuse clouds of negative charge called pi orbitals that hover just above and below the flat plane of the ring.
Okay, following.
When you stack the tyrosine rings incredibly close together, which the tight cross-beta fold forces them to do, those electron clouds actually touch and overlap.
So they create a continuous tunnel.
Precisely. The overlapping electron clouds create a shared continuous orbital pathway running down the entire length of the fiber. It allows electrons, or electron holes, to literally hop from one tyrosine residue to the next over vast micrometer distances. The protein is acting remarkably like a synthetic organic semiconductor, but it is assembled entirely from biological carbon-based building blocks.
It isn't just shuffling electrons, right? The framework details proton conductivity too, based on a 2024 paper by Navarro.
Yes, using short prion-inspired peptides, Navarro's team built self-assembling fibers that conduct protons. And they actually conduct them more efficiently than many of the synthetic petroleum-derived polymers we use in industry today.
But why do we care about conducting protons? What does that actually build?
It builds the future of sustainable energy. Proton exchange membranes are the heart of hydrogen fuel cells. Right now, manufacturing those membranes requires complex synthetic chemistry and rare materials.
So this replaces that.
Enfield's framework suggests you could build a massive industrial-scale zero-silicon biofuel cell, where the internal membranes are grown from biocompatible, renewable protein feedstocks. The structure transports the protons via a similar hopping mechanism, but instead of using electron clouds, the protons jump along the dense networks of hydrogen bonds on the surface of the fibril.
Okay, so this programmable thread is a structural composite, it's a copper wire replacement, it's a semiconductor, and it's a fuel cell membrane. But the manifesto goes further. It claims the material is an active power generator. Enfield talks about piezoelectricity. I know Culkin found this back in 2010, and a researcher named Dolai really quantified the power output in 2024. Can we walk through what piezoelectricity actually is?
Piezoelectricity is the ability of certain materials to generate an electrical charge in response to applied mechanical stress, or conversely, to physically change shape when an electrical field is applied to them. It is basically a translation between mechanical movement and electricity.
We use this all the time, right? Like the quartz crystal in a watch vibrates when you apply a battery current, which keeps the time. And the microphone I'm speaking into right now has a piezoelectric element that gets bent by the sound waves of my voice, and it translates that physical bending into the electrical signal you're hearing.
Exactly. We rely heavily on synthetic piezoelectric crystals in ceramics, but discovering this property natively in a self-assembled biological nanotube completely rewrites what is possible. Dolai's team looked at specific 10-nanometer tubes made from diphenylamine peptides. In order for a material to be piezoelectric, its crystal structure must be non-centrosymmetric.
Meaning what, exactly?
It means the crystal lattice lacks a center point of perfect symmetry. If you look at the arrangement of atoms, the positive charges and negative charges are slightly offset from one another.
Okay.
When you physically bend or squeeze the crystal, you force those offset charges closer together or further apart, which creates an electrical polarization of voltage. Because the amyloid fibril naturally twists and folds into an asymmetric directional shape, it inherently satisfies this physical prerequisite.
And according to the manifesto, they can boost this native power output. Enfield mentions that if you mix up the genetic sequence, specifically if you dope the material by adding the amino acid tryptophan into the mix, you enhance that overlapping electron cloud effect we talked about, the pi-p stacking, and it boosts the piezoelectric power output by 38%.
which demonstrates true programmability. You aren't just stuck with the base properties of the protein. You can engineer the molecular sequence to optimize its energy conversion efficiency.
I am trying to wrap my head around this. It's like planting a microscopic seed in a vat of water and watching an extension cord grow on its own. And then you realize the extension cord doesn't even need to be plugged into the wall because the cord itself acts as its own microphone and a battery, generating its own power whenever it vibrates.
It's a perfect analogy.
But I have to stop and ask the obvious grounded question here. Can a wet biological wire ever actually compete with the rigid perfection of an Intel silicon chip or a copper cable? We are so accustomed to the static reliability of our current technology. If a microscopic fracture occurs in a copper trace on my computer's motherboard, the board shorts out and the computer dies. Can a biological wire really be trusted to not just degrade or fail?
It is the most intuitive objection we have because our everyday experience associates biology with fragility. Leaves wither, food rots, skin tears.
Exactly.
But we have to discard that bias and return to the physical indestructibility we discussed initially. These specific cross-beta configurations are not fragile wet biology. They are thermodynamically locked nanostructures, whose chemical stability rivals synthetic plastics. But more importantly, you touched on the exact reason why they are superior to silicon, the motherboard fracture.
Because silicon can't heal.
Exactly. A silicon wafer is a dead material. If it cracks, it is permanently broken. But these biological circuits operate in a state of dynamic equilibrium.
What does that mean in practice?
If an assembled amyloid nanowire is physically severed, you suddenly have two exposed, sticky ends of a fibril. If that wire is housed in a medium containing dormant protein monomers, which the framework assumes those exposed broken ends immediately act as new templates, they grab the free monomers, fold them into shape, and physically regrow the connection across the gap. You are trading the static, brittle reliability of a carved rock for the dynamic, self-healing, regenerative reliability of a living system.
A carved rock versus a living system. That completely changes the paradigm of hardware, which transitions us perfectly to the next leap in Enfield's manifesto. Because if these indestructible fibers can conduct electricity, generate power from vibration, and heal their own circuits when severed, what happens when you use them to process information? What happens when you hook these living wires up to the ultimate biological hard drive?
You are referring to the integration of prion logic gates with DNA data storage. This is where the framework graduates from advanced materials science into the realm of molecular computing.
Yeah, let's talk about the computational soup. Because to really grasp why Enfield thinks this is the future, we have to look at the severe limitations of how every computer on Earth currently works. Your laptop, your phone, the massive server farms running artificial intelligence, they all rely on binary logic.
Yes, the foundation of classical computing. Silicon transistors act as tiny physical switches. They can only exist in one of two states. Electrical current is flowing or it is not flowing. A 1 or a 0. On or off.
It's basically a billion tiny light switches flicking on and off incredibly fast, which works great, but it is fundamentally limited by that binary constraint. Each physical switch, no matter how small we carve it, can only hold a single bit of information at a time. But DNA, the biological hard drive inside every living cell, doesn't work like that. DNA isn't binary. DNA is quaternary.
It utilizes 4 distinct states. The genetic code is written using 4 nucleotide base pairs: adenine, cytosine, thymine, and guanine A, C, T, and G.
Which means a single molecular state change in a piece of DNA can encode double the information of a state change in a binary silicon transistor.
And when you extrapolate that out to volumetric density, the sheer amount of data you can pack into a 3-dimensional physical space, like a cubic millimeter DNA storage, absolutely dwarfs any solid-state hard drive humanity has ever engineered by several orders of magnitude.
Right. I've read those statistics where all the data on the entire global internet could theoretically fit into a shoebox full of DNA.
Easily, yes.
But there has always been a massive catch with DNA computing. Historically, reading and writing data to a DNA strand is agonizingly slow. It relies on chemical reactions. You have to introduce an enzyme, wait for the enzyme to physically float over to the DNA, bind to it, and slowly pry the double helix apart to read the sequence. It can take hours. You can't run a smartphone, let alone a global internet, if it takes 3 hours to load a web page.
You definitely cannot.
But Enfield's framework details a physics breakthrough that completely bypasses the slow chemistry. He talks about using terahertz radiation.
This is a phenomenal application of resonance. Terahertz radiation, or TERS, is an electromagnetic wave that occupies the frequency band right between microwaves and infrared light.
The terahertz gap, right?
Yes, for a long time, researchers didn't really know what to do with the terahertz gap. But what physicists recently discovered is that the hydrogen bonds, those exact same weak attractions we talked about holding the beta sheets together, are also what hold the two strands of the DNA double helix together. And molecular bonds act like tiny microscopic springs.
And every spring has a natural frequency where it wants to bounce.
Exactly. It turns out the natural vibrational frequencies of the hydrogen bonds zipping DNA together fall exactly into this terahertz range.
So instead of waiting for a slow chemical enzyme to float over and pry the DNA apart, you just blast the strand with a highly specific terahertz frequency and the bonds start to vibrate.
They resonate. They absorb the terahertz energy and vibrate so violently that the bonds temporarily break. You literally unzip the DNA strand using pure light in trillionths of a second, picosecond.
That's incredibly fast.
The moment you turn off the terahertz pulse, the physical structure snaps back into its lowest energy state and the DNA zips back together. You're using light to perform read and write operations at speeds comparable to modern silicon processors, but on a physical medium that uses quaternary logic and possesses near infinite storage density.
But here is the major interconnect problem that Enfield solves. You have this miraculous, lightning-fast DNA memory. But how do you wire it together to actually build a computer? You can't take a soldering iron and attach a copper wire to a single DNA molecule. The dimensional scales are completely mismatched.
And that dimensional mismatch has been the graveyard of organic computing for decades. Even our most advanced silicon features, carved with extreme ultraviolet lithography, are massive, clumsy structures compared to the elegant precision of a single molecule.
Right.
If you try to build a hybrid system, an inorganic copper wire talking to an organic DNA strand, the physical interface between the two is always the bottleneck. The signal degrades.
Enter the prion fibers.
Precisely. Because the engineered amyloid fibers naturally self-assemble at a width of around 10 nanometers, and because they can be programmed to grow into specific topologies and attach to specific molecular targets, they serve as the perfect physical interconnects. You use the self-wiring internal conductive protein threads we discussed earlier to physically link the DNA memory sites together.
So both the memory and the wiring exist at the exact same native molecular scale. Enfield calls this the computational soup. The DNA acts as the high-density memory. The prion fibers act as the physical interconnects, the logic gates, transferring the data. And the high-speed terahertz pulses act as the clock signal driving the entire system. It sounds like the ultimate self-building liquid brain.
It really does.
But wait, I see a massive physics problem here. Anyone who works with wireless technology or airport scanners knows that terahertz radiation is notoriously incredibly sensitive to water. Water absorbs terahertz waves instantly. It's why those airport scanners can only see the surface of your skin. The water in your body blocks the rest.
That is true.
If this is a biological soup, meaning these components are floating in an aqueous solution, how on earth do the terahertz pulses actually reach the DNA without being absorbed by the liquid? Wouldn't the water in the vat just absorb all the energy, heat up, and boil?
That is a critical engineering hurdle, and it is exactly why you cannot simply blast a bulk terahertz beam into a vat of liquid and expect it to work. Enfield addresses this directly through a mechanism called nanoplasmonic focusing. You don't illuminate the whole vat. Instead, you integrate an array of microscopic nanoantennas, typically made of bismuth or gold, directly onto the protein scaffold near the DNA.
Microscopic biological TV antennas.
Essentially, yes. These antennas are tuned to capture the incoming ambient terahertz field. When the wave hits the antenna, it excites the electrons on the surface of the metal, creating what is called a surface plasmon.
Okay, a surface plasmon.
This effect concentrates and funnels the massive terahertz wave down to a sub-wavelength scale, focusing the energy into an incredibly intense, localized hotspot, right exactly where the DNA strand is positioned. And crucially, the immediate microenvironment around that antenna is maintained in a near-dry or highly structured state by the protein scaffold. You bypass the bulk water absorption entirely by capturing the energy and routing it with nanoscale precision.
That is an elegant solution. And because we are talking about using prions as the actual logic OSICs transferring this data, it isn't just a binary system of switching on and off.
No, it introduces non-binary conformational logic. A silicon switch only has two states, but a complex prion protein can occupy multiple stable, distinct folded states. And because of its intrinsic templating nature, the disease mechanism we discussed at the start, a conformational change in one protein physically cascades down the line, physically modifying the folded state of its neighbors.
So the signal isn't just passing through a dead wire. The wire itself is reacting and changing shape as the data moves through it.
It modulates and amplifies the signal. It is a form of analog mechanical processing that behaves much more like the complex cascading action potentials in a human neural network than the rigid linear calculations of a digital computer.
And the framework even touches on the quantum frontier to make these signals move faster. Enfield explores the theoretical potential for something called ballistic phonon transport. Can we unpack what a phonon actually is?
It requires a slight shift in how we think about energy. We usually think of heat or sound traveling through a material by atoms physically bumping into one another. A phonon is a collective vibrational excitation.
Meaning?
It is a quantized ripple of mechanical energy moving through a lattice of atoms.
Yeah.
Usually when a phonon travels through a material, it scatters. Imagine playing pinball. The ball is the energy and it is constantly hitting the bumpers, the imperfections in the material. Every time it hits a bumper, it loses energy, generates friction, and changes direction. That is scattering.
But ballistic transport? Ballistic implies a bullet.
Ballistic transport is like playing pinball after someone removed all the bumpers from the table. Because these engineered amyloid fibers are quasi-one-dimensional structures, meaning they're incredibly long but only a few atoms wide, and because their hydrogen bonds are arranged in an absolutely perfect, repeating, mathematically precise periodic lattice, it is theoretically possible for a phonon to enter one end of the fiber and glide perfectly to the other end without hitting a single atom out of place.
Meaning it travels without scattering, without losing any energy to friction or heat.
Mechanical superconductivity, zero-loss energy transfer. And when you combine that perfect periodic lattice with the tyrosine-hopping electron clouds we discussed earlier, materials scientists are deeply investigating whether these specific protein structures could eventually support true molecular electron superconductivity under ambient conditions.
That's just mind-blowing.
It is highly theoretical right now, but the fundamental physical prerequisites are structurally present in the material.
Okay, let's take a breath and zoom out. We have conceptually built an indestructible, self-healing, liquid-state molecular computer that acts as its own wire, its own battery, and processes data using terahertz light and quantum zero-loss mechanics. It's astonishing. But right now, we are still talking entirely about the nanoscale.
Yes, the invisible world.
We are talking about things so small you need an atomic force microscope just to verify they exist. How do we take this molecular magic trick and scale it up? If I want to build a bridge or a house or a spaceship out of this material, how do you cross the gap from the invisible microscopic world to macroscopic engineering?
We must transition from the realm of quantum physics and molecular biology into the realm of macroscopic industrial engineering. The key concept that bridges that gap in Enfield's framework is what he calls the seeding paradigm.
Let's explore the seeding paradigm because the way Enfield describes it, it sounds less like a manufacturing process and more like an industrial cheat code.
It fundamentally upends the thermodynamic economics of how human beings make things. Think about how we produce macroscopic structural materials today. To make high-tensile steel, you have to run heavy diesel machinery to mine iron ore out of the earth. You have to transport it across oceans.
And then smelt it?
And then you have to put it into a blast furnace and smelt it at 2,500 degrees Fahrenheit to burn off the impurities. The sheer amount of fossil fuel energy required just to reach the melting point of steel represents a hard, inescapable thermodynamic floor.
It's expensive, it creates massive emissions, and you can only do it in a giant, centralized factory.
Now look at the seeding paradigm. To create tons of this engineered amyloid composite, you do not need precision laser cutters or smelting furnaces. You need a massive bioreactor. Think of a giant stainless steel brewing vat, like you would see at a commercial beer brewery.
Okay, a big vat.
You fill that vat with an aqueous solution water that is rich in nutrients and contains the unfolded, free-floating monomer proteins.
Which you can harvest from genetically modified algae or cyanobacteria, right? Just growing in ponds using sunlight.
Exactly. The raw feedstock is practically free and infinitely renewable. So you have a vat full of these loose proteins. Left alone, they might take years to spontaneously fold. But then you introduce the cheat code. You drop in a tiny microscopic fragment of an already formed cross-beta fibril. This is the seed,
The template.
the template. As the free-floating proteins in the vat bump into the exposed ends of that seed, the physical geometric shape of the seed exerts an electrostatic force that physically forces the loose protein to fold and snap into the exact same cross-beta shape, locking onto the end and extending the fiber.
But if it's just growing one long string from the end of a seed, that would take forever to fill a commercial vat.
Which is why the bioreactor is mechanically agitated. It has large paddles that constantly stir the liquid. As the fibers grow longer, the physical shear force of the spinning paddles snaps them in half.
Oh, wow. And every single time a fiber snaps in half.
You now have two exposed ends instead of one. Every single broken fragment instantly becomes a new seed, pulling in monomers from both ends, growing, and snapping again. It becomes an exponential cascading chain reaction of self-replicating growth.
That's incredible.
You are effectively growing skyscraper components, space elevator cables, and bulletproof armors at room temperature in a vat of water, utilizing carbon dioxide and sunlight as your ultimate power sources.
So instead of a fiery, deafening industrial foundry, your manufacturing base is a quiet, bubbling biological brewery. And because the material is built on this logic of seeding and regrowth, it retains that property even after you form it into a solid object. The framework goes into deep detail on self-repairing structural composites. It uses the biological example of E. coli curly fibers.
All right, curly fibers are a specific type of functional amyloid naturally produced by bacteria like E. coli. The bacteria secrete these proteins to weave a dense, tough protective mesh around themselves, called a biofilm. The biofilm is their armor. What researchers observed is that if you physically scratch or crack that biofilm, the broken ends of the curly fibers are suddenly exposed to the surrounding environment.
Just like the snapped fibers in the bioreactor.
Exactly the same mechanism. If the bacteria are still secreting loose monomers into that environment, those free monomers drift into the crack, hit the exposed broken ends of the fibers, and immediately template new growth. The fibers literally bridge the gap, weave themselves together, and seal the crack.
So take that biological principle and apply it to aerospace engineering. You could have a spacecraft pressure hull built from a macroscopic amyloid composite. But within the matrix of the hull, you embed microscopic channels filled with a fluid containing dormant protein monomers. If a micrometeorite slams into the ship and punches a tiny microscopic fracture in the hull, it physically breaks the amyloid fibers. Those broken ends are now exposed to the dormant fluid. The fluid activates, the fibers act as seeds, and the hull literally scabs over and heals its own fracture in the vacuum of space before it can compromise the structural integrity.
The primary engineering challenge at that stage is tuning the growth kinetics to match the required damage repair rates. But the fundamental biological proof of concept exists and functions in nature today.
Okay, so we can brew a self-healing spaceship in a giant vat. But Section 8 of Enfield's framework goes somewhere even more visceral. We have to talk about food technology, the concept of protein lattice printing.
This often elicits the strongest reaction because it applies this profound industrial technology to the most intimate aspect of human survival, eating. The framework proposes using the exact same templating cascade mechanism to engineer meat analogs.
So using a prion-like chain reaction to literally grow a synthetic steak.
Conceptually, yes. But to be absolutely unambiguously clear, we are not talking about feeding people disease-causing proteins. The framework relies heavily on synthetic biology to design entirely novel, safe, highly digestible protein sequences that merely utilize the physical self-assembling trick of the beta sheet to build complex three-dimensional structures.
But how do you give it the shape of a steak? A vat of growing fibers just produces a slurry, right? Enfield talks about a process called optogenetic lithography. So it sounds like a 3D printer, but it isn't extruding hot plastic goo out of a moving nozzle.
Nozzle extrusion is far too crude for biological mimicry. Optogenetic lithography uses light. You start with a vat of engineered protein monomers. But these specific monomers have been modified with light-sensitive chemical switches. They remain completely liquid and dormant in the dark.
Okay, light sensitive.
But when you shine a highly focused laser, say, an ultraviolet or visible light beam into a specific microscopic coordinate within the vat, the light triggers the chemical switch on the proteins in that exact coordinate.
They cure into solid form, voxel by voxel, wherever the light touches them.
Exactly. You sweep the laser through the liquid vat in 3 dimensions, and wherever the light intersects, the proteins snap into the cross-beta architecture and lock together. You are directing the folding cascade with molecular precision.
Snapping together microscopic bundles of synthetic muscle like molecular Legos.
The reason a modern plant-based burger doesn't quite replicate the mouthfeel of a real cut of beef is because it lacks the microscopic structural geometry of animal muscle, the incredibly specific alignment of muscle fibers, fat matrices, and connective tissue. By using light-activated lithography, you can dictate exactly where and how the amyloid scaffold forms, recreating that complex microarchitecture layer by layer without a single cow or pig ever being involved.
Wait, I have to step in here. We just spent a significant amount of time establishing that the cross-beta architecture is the ultimate impenetrable shield. We talked about the phalanx formation. We said it survives pure boiling acid because the peptide bonds are physically hidden from protease enzymes.
We did.
If we use light to print a perfectly textured synthetic steak out of this exact same molecular structure, how on earth is my stomach going to digest it? Wouldn't the material be immune to human stomach acid? Are we just going to eat this incredibly tough, indestructible material and have it sit in our guts like a swallowed Lego brick?
It is a vital question, and it highlights the genius of the HBD dial, the hydrogen bond density dial we discussed earlier. The cross-beta architecture is not just one monolithic thing, it is a programmable platform. The sequences are tailored specifically for their application environment.
So you change the code.
Exactly. If you are building a submarine pressure hull or the exterior plating of an aerospace vehicle, you absolutely program the sequences that form the tightest, most indestructible, protease-resistant variants possible. But if you are printing a consumable food lattice, you program completely different sequences. You design a protein chain with a deliberately lower hydrogen bond density. More importantly, you engineer specific exposed enzymatic cleavage sites directly into the flexible side chains.
You deliberately leave gaps in the phalanx formation so the stomach acid can get in.
Precisely. The food lattice uses the self-assembly mechanism to perfectly mimic the physical texture and bite of animal muscle. But it is built from sequences that human digestive enzymes can easily access and break down into standard, nutritious amino acids. The geometry is programmable, and its eventual degradation is equally programmable.
So imagine the implications for deep space exploration. NASA could send a dormant vat of dried algae-derived protein powder and a light printer on a multi-year mission to Mars. The astronauts could add water, turn on the lasers, and print a perfectly textured, nutritionally complete ribeye steak for dinner. And the next morning, using a different protein powder in the exact same printer, they could print a replacement structural panel for a damaged airlock.
It's all the same source material.
The food and the spacecraft are woven from the exact same fundamental technology.
The versatility is entirely unparalleled in modern material science, which brings us to the ultimate extreme environments discussed in the framework. We have covered how we build our macroscopic environment and how we produce our food. Now we must look at how this material operates at the absolute outer limits, acting dynamically inside the living human body at the microscale and operating outside the Earth's atmosphere at the macroscale.
Let's start by looking inward at the biomedical applications. Enfield points out that the physical shape of these self-assembled fibers makes them incredible vehicles for drug delivery. Specifically, their high aspect ratio. They are incredibly long compared to their width. They look like microscopic needles.
The physical geometry is vital for interacting with cellular biology. Historically, oncology has tried to deliver targeted cancer drugs using spherical nanoparticles. You build a microscopic hollow ball, fill it with toxic chemotherapy drugs, and hope it enters the cancer cell. But a sphere is a difficult geometry for a cell membrane to absorb.
Because the cell has to swallow the whole ball at once.
Yes. But a long, thin, rigid, needle-like structure interacts with the cell membrane entirely differently. It slits into tumor cells via a biological process called macropinocytosis.
Macro meaning large, pino meaning drinking.
Correct. The cancer cell is essentially taking a big gulp of its surrounding fluid to scavenge for nutrients to fuel its rapid growth. When it gulps, the long, thin amyloid fiber is easily swept up. Because of its needle-like shape, it penetrates the membrane and slides into the interior of the cell much more efficiently than a bulky sphere of equivalent volume.
And once it's inside the tumor cell, the framework gets truly futuristic. Because of the piezoelectric properties we talked about, the ability to generate electricity from vibration, Delai's 2024 study demonstrated something called wireless cancer therapy. You don't even need to fill the fiber with a toxic chemo drug.
This is a profound conceptual leap in oncology. You inject these specific, non-toxic piezoelectric amyloid fibers directly into the tumor site. Because the proteins are entirely biocompatible, they provoke no immune response. They just sit there harmlessly inside the cancer cells. Then the clinician applies an external, non-invasive ultrasound field to the patient's body.
Just standard sound waves from an ultrasound wand like you'd use to look at a baby?
Yes, the acoustic energy from the ultrasound waves travels harmlessly through the healthy tissue. But when those sound waves hit the tumor, they physically vibrate the amyloid fibers that have accumulated inside. Because those fibers are piezoelectric, that rapid physical flexion generates a localized electrical voltage up to 1 volt per fiber.
So you have a microscopic power plant generating electricity inside the cancer cell.
And that localized electrical charge drives rapid oxidative chemistry in the immediate fluid surrounding the fiber. It strips electrons from water and oxygen molecules, generating what are called reactive oxygen species, or ROS. Highly concentrated free radicals. ROS are violently unstable molecules. In high concentrations, they immediately shred the DNA, proteins, and lipid membranes of the cell they are inside.
They destroy the cancer cell from the inside out.
Precisely. You achieve a completely wireless, targeted therapy. The biological fiber acts as an acoustic to electric transducer and a localized chemical catalyst. You turn on the ultrasound, the fibers electrocute and chemically burn the cancer cells to death from the inside. And when the treatment is done and the ultrasound is turned off, the fibers simply degrade into benign amino acids that the body clears naturally.
Incredible.
There are no implanted power sources, no heavy metals, and zero systemic chemical toxicity to the rest of the patient's body.
So what does this all mean? We have a material that is a microscopic acoustic weapon against tumors. But in the very same breath, Enfield pivots from the microscopic interior of a tumor to the total opposite extreme of physics. He talks about deep space propulsion, specifically a prion EM drive architecture for spacecraft.
It is a jarring pivot, I agree. But conceptually, the physical connective tissue is absolute. Advanced theoretical propulsion concepts like gravitomagnetic field generators or vacuum perturbation drives all share a common engineering bottleneck. They require the generation of incredibly intense, highly structured, rapidly oscillating electromagnetic fields.
Right.
And generating those fields exposes the engine's components to environments of extreme thermal stress and intense ionizing radiation.
If you are running an engine that theoretically bends the local geometry of space-time to move a ship, you are dealing with massive radiation and heat that would melt conventional components. A standard copper wire coil would vaporize instantly under those loads, but the cross-beta amyloid lattice survives.
It survives the environment, yes, but it does something much more profound. It actively shapes the physics of the engine itself. Enfield discusses a phenomenon called embedded chirality.
Chirality just means handedness, right? Like how your left hand is a mirror image of your right hand, but you can't superimpose them on top of each other.
Exactly. When we look at the physical molecular structure of these assembled fibers, they're not perfectly straight, smooth cylinders. As the beta sheets stack and lock together, the subtle physical bulk of the amino acid side chains forces the entire structure to twist. It naturally forms a physical helix, and it always twists in a specific direction.
Always.
Yes, infectious mammalian PRP has a left-handed twist. Many engineered functional amyloids have a right-handed twist.
It's basically a microscopic spiral staircase.
Yes, and here is where the physics converge. In electromagnetics, when you run an alternating electrical current through a helical or spiral-shaped conductor, the resulting magnetic field inherits the physical geometry of the wire. A left-handed twisted wire naturally produces a left circularly polarized magnetic field.
It's like the shape of a riverbed naturally creating a whirlpool. You don't need to install a mechanical pump or a paddle wheel to make the water spin. The twist is literally built into the ground itself. The water has no choice but to follow the shape of the terrain.
That is a perfect analogy for embedded chirality. In a vastly complex macroscopic EM drive, instead building massive, incredibly heavy external magnetic coils to mechanically shape the field into these complex topologies, you just construct the engine's waveguides using a metallized prion lattice.
Wow.
The physical chirality of the molecule automatically, passively dictates the precise helicity of the electromagnetic field it produces. The material is the field architecture. Whether it is acting as an acoustic transducer inside a human tumor or an electromagnetic waveguide in a vacuum field, the core underlying principle is identical. The physical geometry of the molecule dictates the macroscopic physics it produces.
Okay, I hear the physics, but I have to stop you because using biological material, even miraculously tough biological material inside an engine that generates warped geometries or massive thermal loads sounds genuinely insane. I know we talked about it surviving boiling water, pure acid, and gamma radiation, but an advanced propulsion drive. Wouldn't the sheer thermal load thousands of degrees just instantly vaporize the carbon atoms cross beta shield or not?
It is the ultimate extreme environment, and naked proteins would absolutely incinerate. But you must remember the composite nature of the framework. We're not talking about naked protein fibers floating unprotected in a void. In an aerospace engine, we're talking about heavily metallized amyloid lattices embedded within complex thermal management matrices and leveraging the dynamic self-repairing continuity we discussed earlier.
Oh, I see.
The amyloid fiber provides the precise structural template and the geometric chirality for a surrounding liquid metal or high-temperature conductive element. Its incredibly low coefficient of thermal expansion keeps the electromagnetic field geometry perfectly stable as temperatures fluctuate. And if microscopic fractures do occur from extreme thermal shear stress, the dormant matrix undergoes rapid seeded regrowth to instantly heal the conductor continuity. It is applying the resilient paradigm of biology to solve a rigid physics problem.
Which finally brings us to the elephant in the room. We've danced around it for an hour, but we have to tackle the containment problem. By now, anyone listening is likely marveling at the sheer scope of this technology. It sounds like magic, a material that can cure cancer, build spaceships, compute data at light speed, and feed astronauts. But there is a very dark, very heavy shadow hanging over the word prion.
The shadow of fatal neurodegenerative disease. Mad cow disease, Creutzfeldt-Jakob disease in humans, Kuru, chronic wasting disease, which is currently devastating deer and elk populations.
Exactly. These are horrific, currently incurable, 100% fatal diseases caused by infectious mammalian prions, specifically the misfolding of the human PRP protein. If this industrial technology scales up globally, if we have vats of self-replicating prion-like proteins in every city, are we talking about triggering a global biological catastrophe? How do we ensure we don't accidentally Grey-Boo the planet with an indestructible brain-eating protein?
This raises an important question, and it is the single most important question to ask. Enfield's framework addresses the containment problem explicitly and head-on. The resolution lies in absolute, uncompromising genetic sequence segregation.
Segregation.
The proteins utilized in these engineering applications for the computers, the ship hulls, the fuel cells, the food, are emphatically, biologically, completely separate from the mammalian PRP prion.
They use the yeast ones, like Scheibel did with the gold wire?
Yes, they utilize yeast prion determinants like SUP35 and UR2, as well as entirely synthetic, non-natural peptides, like the X-tire sequences engineered for proton conductivity. These engineered molecules share the structural logic of self-assembly, the physical trick of the cross-beta architecture, but they possess absolutely zero binding affinity or pathological capability in human biology.
So it's the difference between studying how a venomous snake's fang physically works so you can invent a better, painless hypodermic needle for hospitals versus actually injecting people with snake venom.
A very precise comparison. We actually do this in modern medicine today quite routinely. We use the self-replicating, cell-infiltrating logic of retroviruses like HIV to create life-saving targeted gene therapies. We engineer the virus shell to deliver a genetic cure rather than a fatal disease.
Right. That makes sense.
The engineering borrows the elegant mechanism of the biology. It does not import the pathology. And with the advent of modern CRISPR base editing and AI protein folding models, researchers can design, simulate, and verify these safe, target-specific sequences in a matter of days. They can ensure, at the fundamental genetic level, that the synthetic amyloids used in a bioreactor completely lack any molecular mechanism to interact with human neurological proteins.
So we have the mechanism isolated, and we have mathematically verified its safety. Let's talk about the timeline Enfield lays out in the manifesto, because he is projecting some incredibly aggressive milestones for rolling this out.
The framework maps a clear industrial progression from 2025 all the way to 2060 and beyond. Between 2025 and 2030, the focus is strictly on scaling up industrial fiber production and perfecting the biomedical biosensors. This phase is largely already happening in university laboratories.
Okay, the immediate future.
Right. By the 2030 to 2040 decade, the projection moves to macroscopic structural elements, aerospace panels, self-healing drone chassis, and the deployment of space-rated food printers.
And then the big one, 2060 plus. Full planetary-scale civilizational integration. A civilization essentially woven entirely from programmable biological fiber. No, wait a minute. I have to look at this pragmatically. A zero marginal cost supermaterial that grows in giant vats of algae sounds like an absolute economic miracle. I buy the physics and I buy the chemistry. But isn't a 2060 timeline for complete civilizational integration incredibly, almost naively optimistic? Have you met human bureaucracy? The regulatory hurdles just for approving a new food dye take a decade, let alone replacing the entire Silicon Valley microprocessor industry and the global steel supply chain with self-replicating vats of prion logic goo. The red tape alone will take 50 years.
The regulatory friction will be immense, absolutely. There will be public fear, Senate hearings, and massive pushback from legacy industries. But history shows us that sheer economic and strategic imperatives can act as unstoppable forcing functions.
Bottom line.
Look at the energy floor we discussed earlier. The energy cost of smelting steel or fabricating silicon wafers in a clean room is dictated by the laws of thermodynamics. It will never be cheap. But the energy cost of bioreactor-grown amyloid approaches zero as you scale up photosynthetic algae feedstocks. The raw economic pressure of a material that is 10 times stronger than steel, lighter than plastic, computes data at terahertz speeds, and is practically free to grow will simply overwhelm conventional industrial inertia. Capitalism abhors an inefficiency.
So the sheer gravitational pull of the economics will drag the regulations along with it, kicking and screaming.
The economics and the space race. Aerospace applications, specifically the extreme deep space requirements of NASA and commercial spaceflight, will act as the ultimate accelerant. When the cost of launching mass into orbit is the primary bottleneck for becoming an interplanetary species, a technology that allows you to launch a tiny vial of seed proteins and a lightweight vat of dehydrated algae, and then autonomously grow your habitat, your computers, and your food on the surface of Mars, becomes strategically non-negotiable.
Okay, let's step back and look at the entire board of what we've covered today. We started this hour talking about a disease, a microscopic, terrifying glitch in biology. And we have meticulously watched Enfield's framework unpack that glitch, dissect it, and reverse engineer it into a universal design architecture.
We really have.
We've seen how the dense, hydrogen-bonded cross-beta scaffold creates an indestructible, flexible nanocomposite, how it naturally wires itself into highly conductive electrical grids and terahertz-speed, liquid-state DNA computers. We explored how it can be grown exponentially in vats to build self-repairing spaceship hulls, or intricately patterned by lasers to print perfectly textured food. And we saw how its very molecular chirality can act as an acoustic weapon to electrocute cancer, or shape the raw magnetic fields of an advanced propulsion drive.
The overarching theme of the framework is total convergence. The cross-beta scaffold is not just a new category of material like plastic or carbon fiber. It is a programmable substance that fundamentally irrevocably blurs the line between a living organism, a mechanical machine, and physical infrastructure.
It completely changes how you look at the engineered world around you. The next time you hold an incredibly complex piece of technology, like an advanced microchip, or you look up at a towering steel skyscraper, I want you to realize that the future of those exact technologies might look less like a fiery foundry or a sterile, vacuum-sealed clean room, and much more like a quiet, bubbling biological brewery.
We are slowly transitioning from carving our technology forcefully out of dead rock to coaxing it to grow from the fundamental, self-assembling codes of life.
It leaves you with this profound and honestly almost unsettling thought to mull over. If our hyperfast computers, our daily food, our deepest space halls, and our internal life-saving medicines are all eventually woven from the exact same self-assembling, programmable biological fiber, well, the conceptual boundary between technology and nature completely vanishes. We wouldn't just be using external machines anymore. We would essentially be living as symbiotic cells, interacting and coexisting inside a single programmable planetary-scale organism.
It is a radical reframing of what it means to build a civilization. We are no longer imposing our will on the material world. We are programming the material world to build itself.
It really is. Thank you for joining us on this deep dive into the ultimate universal material. And remember exactly where we started today. That muddy, terrifying world of a medical diagnosis where a biological glitch seemed like the ultimate unstoppable enemy. It turns out that glitch wasn't an enemy at all. It was just a brilliant instruction manual waiting for us to figure out how to read it.